Section 5.6, Intermediate Algebra, Factoring Sums or Differences of Cubes. We have seen that a difference of two squares can be factored, but a sum of two squares is usually prime. The situation is different with cubes. The difference or sum of two cubes can be factored. To see this, consider the following products. If we have a plus b, the binomial, times a squared minus ab plus b squared, and we multiply this binomial times this trinomial, we'll start with taking a times each one of the terms in the trinomial. So a times a squared is a to the third. A times minus ab is minus a squared b. A times the last term is an ab squared. Then we've multiplied everything by a. We'll multiply the rest of these by b. B times each of the terms in the trinomial gives us an a squared b. B times minus ab gives us a b squared with the a, but a minus, so it's a minus ab squared. And we have a b times the b to the second gives us a plus b to the third. Simplifying by combining like terms together, there is no other term other than this first one that has a to the third power. And a squared b is here. We have a minus a squared b plus a squared b. These are opposites, and so they would cancel one another out. And ab squared has a similar ab squared term here, but they're also opposite signs. They cancel one another out, leaving the only other term are b to the third power. We call this a sum of cubes, and it is the result of this special trinomial times this binomial. These products allow us to factor sums and differences of cubes. And note the location of the plus and the minus signs. So when we're factoring a sum of cubes, it results in the cube root of the first term, same sign, cube root of the second term, times the square of the first term, opposite of the sign we have between the two, the product of these two terms in the binomial, plus the square of the last term. And when we have a difference of cubes, essentially the same pattern. It's the cube root of the first term, same sign, cube root of the second term, square of the first term, x squared is x squared, opposite of what we have between the two, so it'll be a plus, product of the two cube roots, so it's xy, and then the square of the last term, negative y squared is plus y squared. And this is the form that we will use to help us factor differences of cubes or sum of cubes. Let's take a look at some examples. So here we have two terms. It's clearly not a difference of squares. It's not a sum of squares because we have a cube. The cube root of x to the third power is x. Is 8 a perfect square? What times what times what gives us 8? We have a 2. We have a sum of cubes. We'll use that pattern that we just wrote down there on our class notes, which is cube root of the first, the sign between the cubes, and cube root of the second. The trinomial then is square of your first term, so x squared is x squared, opposite sign, multiply the cube roots of each, so x times 2 is 2x, and then square the last term. If you multiply the binomial times the trinomial, it should multiply to give you that sum of cubes. In this next example, it's two terms. It looks like a difference of squares, but 27x to the third is not a square. Is it a difference of cubes? 27x to the third is 3x, the quantity raised to the third power. If you take 3x times itself 3 times, you'll generate a 27x to the third. And 64 happens to be 4 to the third power as well. So we do have a difference of cubes. It factors into the following form: the cube root of the first term, the same sign that's between the two terms originally, and the cube root of the second term. For the trinomial, it is the square of the first term. 3x times 3x is 9x squared. Opposite of the sign, the product of the two terms is our next term. 3x times 4 is 12x. And square the last term. Negative 4 times negative 4 is a positive 16. And again, if you multiply the binomial times the trinomial, you should result in this, what we call a difference of cubes. In our next example here, is this a difference of cubes? The variables to the third power is definitely a clue. Here we have 64 again, which is 4 to the third power does give us 64, and m to the third power, the cube root would be m. 27 we just saw in the previous example, that's a 3n is the cube root. Once we have established that it is a difference of cubes and we know what the cube roots are, we're ready to factor. The cube root of the first term, same sign, cube root of the second term. The trinomial is of the pattern square the first term. 4m squared is 16m squared. Opposite sign, multiply the two terms together, so we'll have a 12mn, and then square the last term. We'll add on a 9n squared. In this next one, looking for a sum of cubes perhaps, 27c to the third is a 3c. That one's pretty easy. Have to do a little digging here and perhaps get your calculator out. It turns out 7 times 7 times 7 is 343. So we have a sum of cubes in this problem. It will factor into the cube root of the first, which is 3c, the same sign that's between the cubes, and the cube root of the second term. The rest of this is the square of the first term. 3c squared is 9c squared. Opposite sign, product of the two, 21c is the result of 7 times 3c, and the square of the last term, which is 49. In this last example, they're asking us to factor. It can't be a difference of squares, even though this could be a square. A to the sixth is factors into a to the third times a to the third, or it could be a difference of cubes, and it has to be a difference of cubes. 8 is not a perfect square. Given a choice, it's generally better to factor as a difference of squares before factoring as a sum or difference of cubes, but in this one we don't have that option. It's not a difference of squares because of the 8. So the only other option is it a difference of cubes? Well, a to the second times a to the second times a to the second is a to the sixth. 2 to the third power is 8. So this also is a difference of cubes. So we will take the cube root of the first term, same sign, and the second cube root. Square the first, which is, put an a first, a to the fourth power, change the sign, multiply the cube roots together, so we have a 2a to the second, and square the last term, which ends up giving us 4. Multiplying these together, we look to see anytime if we can factor further. Multiplying to check, yes, it does generate back what we have. Anytime you have a power higher than 2, we should be suspicious that we can, or higher than 1, we should be suspicious of factoring further. A to the second minus 2, this is not a difference of squares, 2 is prime. When we have our trinomial here, does this factor further? And if we look, is this a perfect square trinomial? The first term is a perfect square, that's a to the second. Is the last term a perfect square? It is. If we multiply the two together, we have that, but we have to double that, which makes this a 4a to the second. Typically, not always, but typically when you factor a difference of sums, a difference of cubes or squares, the trinomial is not factorable further, but we never know. There's always that possibility, so it's a good idea to check. This doesn't factor. There's no way that we can get factors of 4 that will add up to give us 2. So this trinomial, even though it's suspicious of being possibly factored further, is not, and this would be our final answer.